Are you thinking there's an example of observation which does not involve interaction?
If there was, we probably wouldn't even, like,
Oh,
if there was a way to observe it without interacting with it at all, it probably wouldn't behave like that. It probably would just look like a wave. Or one or the other.
or one or the other. I mean, without observation, it's, you know, it's whatever.
We don't know what it is
We
without
don't-
observation.
yeah.
Have they tried 3 slits?
Yes, in a way. They have what's called a diffraction grating, which isn't 3, but it'll be hundreds or thousands. And I had one in my hand, and of course put it down someplace.
But what prompted me to saying that was a lot of people misunderstand this experiment and think that the observation is just us looking through a window and not interacting with it at all. And the thing that decides whether or not it changes is our perception. Like it knows that it's being watched. Which I think that's not realistic.
Yeah,
I think that
I
there's a
will
lot more
agree.
going on than just us looking at it.
there, you can see the, yeah, that is. It is just too bright in here for this one. We'll get back to it. Ultimately, the way that this is all resolved within quantum physics is they come up with what's known as the wave function. And that observing it through whatever mechanism collapses the wave function into one thing or another. So in case of this right here, let's take that away. What's happening over here is that when the electron hits this, there's now an interaction with something else, the wave function collapses, and the electron becomes a single particle at this point. And so what you're doing is looking to see where you've got a whole bunch hitting here, if you were hitting there, if you were there. As if it were a wave until it got to the screen. I don't want to ignore what you said, John, but I'm not quite sure really how to.
Right. I mean, it's nothing that.
So in retrospect, you're shooting a beam through there and you're checking the beam, how they relate to another point. Because you got a splitting thing, you're shooting a beam through there, and you want to see how they're reacting on the other side of the matrix that you made to see
Okay.
that if it's a wave or a particle.
Right. Is there a question in that? Or
I'm
you're
just,
summarizing?
that's what you are observing, because you producing a beam, you producing a light, and you looking at how the light reacts on the whatever the other medium that you call to see if it's a particle, because that's the electrons.
How are we producing the light? The light is being reflected into our eye.
Right, but you are producing it by, say, that light beam, whatever tool they use to produce a light beam.
Yeah, that they could.
Yeah,
could probably-
you can't produce electrical electron because it's invisible unless it's a light.
Oh, no,
Electron is.
all right, so
it's
what you're
floating.
seeing, when the electron part of the experiment, what's happening is that when the electron as a charged particle hits,
Right.
this medium right here has to have some sort of scintillation effect, so that
Right.
when an electron hits it, it'll glow. So that's what you're seeing here is the interaction between the electron and the wall,
Right.
or whatever the material this is.
But you have to have some kind of thing to produce that electron through that medium.
Right, and we can collect electrons, whatever it happens to be. If I take a metal surface and shine a light on it at high enough frequency, I got a bunch of electrons coming
Right.
off of it, and then we just sort of, not collect them in a jar, but
I have a mason jar.
Just
Fireflies.
make sure you close it really quickly.
Physics fireflies.
Oh, that'd be so cool if you could do that. All right, anyway, so you basically, as electrons come shooting off, you could then put them into some sort of containment unit, get them zipping around a ring or whatever it is, just apply enough the right magnetic field or electric field to get them always curving the right way. So we can collect electrons. Or you send a hydrogen atom through a strong electric field and the electron gets ripped away from it, since it has only one electron neutrally. And then you have a bunch of protons and electrons. Anyway, awkward transition back. Back to light, which I'll just represent by a gamma. All right, so it's brightest right there in the middle. And then just there's some other spot over here which I'm going to take. So what I want to concentrate on is this spot right here. So we have some central axis. So some distance y. The distance between here is d, traditionally. And if I have two waves going, sort of flashback, when is there constructive interference?
When the two waves meet their peak, or at the
Okay.
same time, their peak at the same
All
time.
right, so we have roughly some constructive interference here. Looks like a little bit of destructive there. This markers. For those who are watching at home, I made it. I would assume they wouldn't believe that, but, all right. Okay, and the distance from here to here is some distance L. Now, in this case that I've drawn right here, I've drawn two different sets of wavelengths, two different frequencies, but over here, we're just dealing with relatively close to a single wavelength of light. Because the laser, that's all the purpose of the laser is to get a concentrated wavelength or concentrated frequency of light. So, as long as they peak at the same time, I have constructed interference. So this is going to be a bright spot if they're peaking at the same point. In other words, the difference between this length right here, which I'll just call L1, and this is L2, the difference between these two lengths should be a wavelength, or some multiple of a wavelength. So this distance right here is equal to a wavelength, or 2 wavelengths, or 3 wavelengths, or some integral number of wavelengths.
I'm guessing that red line you drew right there makes it a right triangle.
It is close enough.
Oh man, at least it looks better than mine.
Now, in reality, it is not really a right triangle, but it is close enough to one so that we could use small angle approximations. So that this angle right here is small.
What's that under it? The wavelength, 2 wavelength?
That distance, the difference between the lengths, these two lengths, has got to be some integer times the wavelength.
Okay.
If it's 0, I guess 0 wavelengths also would be the bright spot in the very middle. So L2 minus L1 is equal to some number, some integer times the wavelength. N is an element of
What is the,
positive integers.
is that a Y up there?
Yes, that's a Y.
I mean, on the top angle, on the top
That's
side.
L1.
L1.
L1, L2. Now, this angle here, I'm going to label as theta. It's pretty darn close to this angle right here. Actually, that's not the one I want. Pretty close to this angle right here, theta. Matter of fact, if I look at I can easily create three right triangles that are primarily along the length of L. If I go from this spot to this spot to this spot, so if I look at that right triangle, and I said that this was roughly theta here, and I'm gonna call this, point A, B, C is directly in line with that. So I have bottom slit, let's give it another label, E, F, and G. I think that's all the major points I need. Oh, wait, no, F, G, and then that's back down in the middle, H. So this is the triangle that goes from E to A to G. If I look at another right triangle there, so from point H to B to G, so the triangle that going from the center, right smack dab between the slits to the point on the wall that's closest to the slits to this point, same point G. This angle is also roughly theta. And then the third triangle is basically the top triangle, and I think that's the letter F right there. Going from point F to C to G. Again, that angle is also roughly theta. Now it seems like I got three triangles all starting in a different spot but end up in the same place. How can they all be the same? I'm not making the claim that they're the same, I'm making the claim that they're close enough to each other that we can get away with saying, close enough. It's physics, not math. The bottom distance here is L every single time.
Is that G down there?
That's a G, yeah. This distance from A to G is just my distance Y here, okay, that Y plus whatever half of D is. In other words, half the slit distance. So this is Y plus 1/2 of D. This distance from B to G is just Y. And this distance from C to G, this little bit right here, is just whatever Y is minus half of D. So my claim that they're all the same angle stems from the idea, or close enough, stems from the idea that D is so small that we can make that approximation. If D is much less than Y, that these are all roughly the same. Bless you.
Thank you.
So I know that the sine of theta is equal to, well, theta small. So that's roughly equal to the tangent of theta, which is just the opposite of the hypotenuse, which is, in the middle case, y over L. If I look at my right triangle right here, my pseudo right triangle, this distance here between them is D. This is, we'll get this triangle right here. So this is point F, E, and some point on there. It said that angle is roughly theta. So the sine of theta in that triangle is the opposite side, which I'm saying is just some integer times my wavelength divided by D, which is the hypotenuse of my pseudo right triangle. And so we have this relationship that n lambda over D is equal to y over L. And so at this point, it depends on how you want to, what you're actually trying to find. If I'm trying to predict y would be n lambda L over D. If I'm trying to find the wavelength, wavelength would be YD over NL, and so on. And just to parallel this, I'm seeing a note I made.
Is that a F or D?
Depends on where you're looking.
I'm like at the wavelength. Wavelength equals YD.
YD over NL. Difference between this and the textbook. Textbook uses the letter X for where I'm using L. There was a lab that we're not gonna do this semester, but there was a lab that we were doing where basically we had various wavelengths of light that were shining up against the wall. And we just kept getting further and further off as we were testing against the expected. And that came down to the fact that at some point, the small angle approximation was not appropriate anymore. And then when we went back to use sine theta instead of y over L, we started getting, again, within 1% of the prediction. All right, so we have a prediction here. Let's see how close we get. So to do this, we need to have a piece of paper up on the board that we can write on, because that seems to work better than marker. And tape, there we go. And I will need some way of holding the laser light still. For the clips.
The N is the, which are on,
Pardon?
the N is,
N is,
Number
basically
one.
which bright spot, the middle bright spot N is 0, the next one is gonna be 1, then 2, then 3, then 4.
okay.
And I'll grab a clip from the other room. All right, so I got light shining right there. Got a Cornell plate in. Hopefully it will stay. Some say that a box is not a flat surface.
Get another one of those clips.
Probably end up doing that, but there we go. Or not.
Off center.
All right. That's probably fine, point enough. All right, so we got a spot there. That is probably sufficient. And we kill the light. There's another point I want to make here. And I'm hoping all of you can see this. All right, so obviously a really bright spot right here where my finger is. As we move out, there's a dark spot here where my finger is now. And then it gets a little bit brighter, and then it gets dark again, and then it gets a little bit brighter, dark again. Can you see those black bands right there?
Yeah.
Yeah.
All right. Nick, can you see them?
Yep.
All right. Within those bands, so if this is a dark band here, and there's a dark band there, where my fingers are. But within that, there's a lot of other tiny little dark bands within it. So what's happening there is the two wave patterns we have going on. So if I mapping brightness here, I got bright, dark, bright, dark, bright. Something like that. And within it, there's a bunch of other smaller bands. The overarching one, the one where I was just pointing out there was the dark band here, dark band here. This is from single slit diffraction, which you observed if you solve the lines between your fingers. And then within it, so it's like a single slit diffraction envelope, and within it is the double slit pattern. So what I've marked here is basically the double slit pattern. So now it's a matter of just measuring. We just happen to have a handy dandy ruler right here. So the distance to, we'll just say the fourth band. So from the central band, from here to here, I'm letting n equal 4. The farther out I go, there's sort of a double edge there. The higher n is, I get greater accuracy because any mistakes, the small mistakes sort of get washed out. At the same time, if I make n too big, I'm suddenly going to start losing the small angle approximation.